Clear?
Yes, sir.
Yes, sir.
Yes, sir.
We left. So we started discussing on this. The third circuit element, we finished on resistance, we finished on capacitance, and the third circuit element, that is inductance, which is basically if a wire is wound over a piece of metal, which is basically the core. Okay, then we have this inductive effect. So the value of this inductance, some of these things is already, we will be recapitulation to you. L is given by mu n square A by S, where mu is mu r mu naught. Again, mu r is the relative permeability of the core. The value of mu naught is 4 pi 10 to the power minus 7 Henry per meter. A is the cross-sectional area of the core on which the coil has been made. It can be rectangular, it can be circular, or it can be of any shape. N is the number of turns, and S is the axial length of the helix. So if you calculate it, the coil will need a certain length, so that is the axial length of the helix. And there will be a voltage across this coil if there is a change in the current. Okay, so the expression for VL is given by L di dt. So so we already know that the voltage will appear across the coil if there is a change in current. It can be due to the value of the current changing, or it can be due to relative motion of the coil and so on. So uh, somehow that flux inside the coil has to change, and that will generate a voltage which will basically oppose the cause. So these things you already know from your school level. So if the value of the current is constant, basically there is no voltage across a coil. So a coil obviously is made of a certain metal. Okay, so once it is and it is basically a piece of wire. So that any piece of wire will have its resistance. So you all know the value of the resistance, the formula of the resistance for a conductor. Now the resistance will anyway be there because it is a metallic piece. But if there is a coil and if there is a change in current, then also some additional voltage drop takes place across it. Okay, so that is be due to the inductive effect. So we did a small example of where we told that if we are given a 3 ohm 3 Henry inductor, the unit of L is Henry, and if this type of a variable current waveform is passed through it. Okay, so what will be generated with variable? So once you have given a variable waveform, it is the x-axis is basically the time axis. So the current value varies with time, the magnitude of the current. So wherever there is a change in the current from that will basically induce a voltage in the inductor. Okay, so then we can plot the
Sir,
yes.
sir, so I doubt that so in when current increases from -1 to 0 in that time interval, then voltage is constant to 3. Then after a sudden it decreases to 0. So does it attains between this value 3 to 0 or direct it goes to 0?
It directly goes to 0, but I couldn't understand the question. Because as soon
Okay.
as it crosses the time t equal to 0, 0 plus the, then if we consider two small intervals, then basically there is no change in current. So the di dt is basically 0. So at once it will become from 0 positive onwards, it will become 0.
Okay, sir.
Okay, so then you can get this type of waveform, and here there is a negative slope, so so there is a negative voltage appearing across the inductor. Now,
Sir,
yes.
if voltage goes sudden 0, then graph should not be continuous.
Which one?
So in the graph, voltage versus current. So voltage goes sudden 0.
So we have shown it, na? In that that the voltage value is 0.
Yeah, yes,
Sir, sir, we denote V is minus L by di dt.
No, that minus or plus will depend upon the whether it is the basic reason is it is opposing the current. Okay, say if you take this current gradient, this is having a positive gradient, here it is having a negative gradient, so it will affect the voltage value. Okay. Hello.
Yes, sir.
Yes, sir.
Yes.
Yeah,
Yes,
Yes,
sir.
sometimes respond
Yes.
because I sometimes having a feeling that as if it got disconnected. Okay.
Yes, sir.
If one or two yes sir, then it's okay for me.
Yes, sir.
So
Yes.
Hello.
yes.
Yes, sir.
Sir,
So
the
we
graph of hello.
yes.
Sir, the graph of voltage should be opposite of the current, na? Like here current is increasing, so voltage must be decreasing there.
No, in whatever way we have basically sometimes you have the positive voltage, so it is on two sides. If you see this side the graph, it is having a positive slope of the current. Okay, so it is di dt is positive. Similarly here there is a negative slope of the current, so it is so it automatically becomes minus. The voltage value becomes minus, and in between t equal to 0 to t equal to 2, it is constant, so the value is 0.
So, but the voltage opposes the change in current, na, sir?
So that has to be shown in the circuit. You know, if I have to plot it, if I have to plot in the magnitude graph, then we can show some convention in whatever way. What will be important is to show one side the positive voltage, the other side negative voltage.
Okay. Okay.
So the value of voltage is given by L di dt. So so if you just if you want to find out I, so just you have to integrate it. Okay, because suppose this L is part of a circuit, and the circuit is suddenly switched on from T naught at T equal to T naught. See, T naught is some time instant. Okay, so up to time T, what will be the current value of the current? Okay, that is current I at IT. As I told in this, wherever there is a changing voltage on current, they are all functions of time. Okay, and so sometimes we may write the function, sometimes we may not write it because they will appear a lot of times. Okay, so the small letter basically indicates it is a varying quantity. So you perform this integration, and then ultimately on the left hand side you get IT minus IT naught. IT naught is very important if at the switching time where the switch was started, if there is a initial current, so that will be also there. But if it is zero, if the inductor is initially, it is called initially relaxed, initially de-energized, so then IT naught will become zero. But if there is some IT naught, it has to be considered. So in general your IT, the current through the inductor at time t, is given by 1 by L integral T naught to T Vt dt. Okay, Vt dt plus IT naught. Okay, we will do lot of these problems. We will see that what is the meaning of this IT naught and all. Uh, uh, we'll see it in actual circuits, but this is how it mathematically comes out of the simple integration. Now, this IT basically, if in indefinite integration, there is going to be some constant which has to be found out. Okay, so if your t, that is t naught, is assumed to be minus infinity, that means where there was no current or energy in the inductor. So sometimes it is called, the inductor is considered to be initially relaxed. That means the time t naught from where you are we are taking as the reference. If it was minus infinity, that means a long time back there was no current in the inductor. So we assume IT naught equal to I minus infinity equal to 0. In that case, your inductor current becomes IT equal to 1 by L minus infinity to T V dt. So the same expression, we just uh, do this integration from minus infinity to T, and this IT naught is initially 0. So we get this simplified expression. So the absorbed power, we know the formula of power P is equal to VI equal to L di dt. Okay, so VI, so if we just substitute V, so which is L di dt, so it becomes Li di dt. And it's just like the capacitance.
Sir,
So,
how will
yeah.
be time minus infinity?
Huh?
How will be the time is minus infinity? How can we take this?
No, so that is the hypothetical. That is how we are. Like suppose you have a piece of inductor and you are going to switch on at say 2 p.m. Okay, and the inductor is there for maybe the last 5 years. So that is the, and it is even before switching there was no current through it. So that is the initially relaxed condition. So before switching there was no current. So that is the initial value of the time, because it is required in integration. You see this, it is required in the integration because it is. So if it is initially relaxed, if there is no current earlier, and just it is switched on, we will actually do the circuits. Okay, so we'll understand. But does it answer your question? Mani is assuming something that is having no current initially from the point of switching.
Yes, I got it.
So the energy accepted by the inductor, it is stored in the magnetic field around the coil. So it is the specialty of the inductor is it generates a magnetic field, and the energy is stored in the coil. Let us do some of this. So V equal to L di dt. So this change is change in energy. Again, as we told that we are doing the computing the energy from T naught to T. So integration of P dt from T naught to T. So you do the integration on the right hand side. So you will get what? Integration I dt is I di will give you what? Integration.
Sir, can you please
I
show
I
the previous
By
slide?
T minus IT square
I
not
square
square
by
by
2
dt.
square by 2 minus IT naught square by 2.
So integration x dx is x square by 2. Okay.
Sir, can you please just show the previous slide, please?
I have to
I
keep the
missed.
previous slide.
Yes, sir, please.
Some of you switch or mute your audio. Okay. If otherwise I will be forced to mute all of you and there will be no interaction, because the background noise actually disturbs the class.
Yes, sir. Thank you.
So the change in energy as we are doing this integration from T naught to T. So all the integration on both sides should be done from T naught to T. And you see here P dt will give on the right hand side L I di dt and dt. So this will cancel out and you are left with L integration of I di, which you all know how to do. So it is half I square by 2. So and putting the upper limit and the lower limit, you get half L IT square minus IT naught square. So the change of energy basically, if the inductor at time t contains an energy WLT, and if it was having some initial energy at T naught as WLT naught, so this change of energy is given by half L IT square minus IT naught square. And so now comes the assumption that if initially there is no current in the inductor, so initially the current in the inductor is assumed to be 0 at T naught. Okay, so if there is 0, so then this IT naught is basically 0. So you are only left with half Li square as the energy. So that is how we get the expression for the energy in an inductor as half Li square. Okay, so obviously you see that this is a function of time. Yes.
So I can't see the screen.
It's visible.
Leave
I'm
the
only
class
seeing
and again join it.
Yeah,
It
so
is visible.
if others can see you must be having some local problem. You have to, maybe you can leave and join and all those things you can try, rather
Excuse
than.
me, sir. Sir, the voltage
in the
across the inductor
now
should
I
be
can see.
minus L di by dt, na, sir?
No, that minus or plus will be the convention, but there is the magnitude of the voltage is L di dt. So that minus 1 plus 2 is just to show that it opposes the current.
Sir, here you are taking the magnitude of voltage.
Yes.
Sign.
Excuse me, sir.
Sign is shown here in the circuit. If you show the circuit, I have given a plus sign. The current is in this direction, so plus is basically the other way.
Sir, in the second equation, sir, WL T naught and minus of half Li I T naught square will get cancelled, na? So why we have to assume that current zero at T naught?
No, at T naught, in the right hand side, see, left hand side is basically the change of energy. Okay,
Yes, sir.
so if your IT naught does not exist, so that is this part is 0. So you are only left with WLT is equal to half Li square.
Sir, but even if it is non-zero, still minus of WL T naught and minus of half Li I T naught square will get cancelled, na? I mean, both
No,
negative terms of both
they are not cancelled. They are basically the same thing. WLT naught is equal to half L I T naught square. So what we
yes,
are actually doing is change of energy. So if your IT naught is 0, basically WLT naught is also 0. So your current energy is basically given by half L I square.
Yes, sir.
Okay, so this I is again a function of time. I have not written the time because it will, every time it is not possible to write the time. But I is basically IT, so you see the WLT is half Li square. Okay, so that is
Sir, can you please explain?
Which one?
Sir, why WL of T naught equals to 0?
If you assume that the WLT naught is basically half L I T naught square. That is the expression of the energy at T naught.
IT, yes, sir.
So if your IT naught is 0, then the WLT naught is basically 0.
Okay, sir.
Okay, so these are actually the formula for the inductor energy, and we have done earlier for the capacitor. So now gradually going to the circuits, that if you have inductors in series and parallel. So if you have inductors in series, if you have n inductors, capital N, in number of inductors, they are connected in series, and it is connected to a voltage source Vs, and since they are in series, the current is going to be the same throughout the inductors. Okay, is it possible to represent the series combination of inductors by an equivalent inductor?
Yes, sir.
Okay, so we have the series combination of inductors, and we are trying to see that what will be their equivalent. So your Vs, if we apply in this circuit, your Vs is equal to the sum of all these individual voltages, and which is nothing but equal to, so V1 is L1 di dt, because it is the same current that is going through this, and obviously it has to be a time varying current. Okay, so L1 di dt plus L2 di dt and so on up to Ln di dt. So since this di dt is common to all, you have this type of expression L1 plus L2 plus Ln di dt. Now,
So why aren't we considering the mutual inductances here?
okay, so those things we will, right now we are only doing the self inductance. Okay, mutual inductance is not there in your first year curriculum. It will be there, some sort of a mutual inductance we will see if once we do that transformer. But eventually it is there for those who you will be doing signals networks in the second year onwards. You will have all those things.
Okay, sir.
Okay, so right now you assume that they are all independent. They don't affect each other. There are n inductors. So for the equivalent inductor, it is basically V equal to Leq. These two expressions, because we are trying to find out if it is possible to express it as an equivalent. So L1 plus L2 to Ln. Okay, so simple thing that inductors in series basically means the equivalent inductor is just the addition of those inductance values. Okay, obviously we are making the assumption as somebody asked about those mutual inductance and all, so I am not going to use those words in this class because it is not in the curriculum. Okay, so only we have considered the self inductances and they are in addition. Similarly, if you have inductances in parallel, okay, so there are n inductances L1, L2 to Ln, and they are in parallel and they are connected to a current source Is. So that current actually gets distributed among the n inductors. Okay, and so the question is it possible to find out a value that is an equivalent value of the inductances in parallel? We have n inductances in parallel. Huh?
In parallel combination, V is a constant.
Can you repeat?
We can add current I8 Is equal to I1 plus I2 till In.
Yes.
And then di by dt.
So your Is is basically summation of In. Okay, so and each of these In is given by this expression. Each of these In is 1 by ln V dt and In T naught, where this small n is varying from 1 to n. Where this small n is varying from 1 to n, and ultimately you get this type of relation. So if you keep all those integrals together, so all these integrals, so across all the inductors, basically the voltage is the same. So that V dt is common to all of them. So it is basically becoming summation of 1 by ln n equal to 0 to n. Then integral of V dt t equal to T naught to T. And then for the second part, again the summation is from In T naught n equal to 0 to n. N equal to 1 to n. Now for the equivalent, it is basically 1 by Leq. So the same expression, but just one equivalent inductance. So what is 1 by Leq? Integral T naught to T V dt plus Is T naught. If there was any T naught, any current during the starting time T naught. So now see, if we are comparing from this, ultimately you get that Leq. You get Leq equal to 1 by so basically it is 1 by Leq equal to 1 by L1 plus 1 by L2 to 1 by Ln. So Leq becomes 1 by L1 plus 1 by L2 to 1 by Ln. Okay, so that is how we can find out. So inductors in parallel basically they behave like the parallel resistances. Whatever formula we have learned to find out the equivalent resistance for parallel resistors happens for inductors in parallel. So as a circuit
we are
element,
not considering. Sir, we are not considering the mutual inductance here, no?
No, I am not. I have never see whatever we are not part of the curriculum. I am not going to use those terms also. Okay, so don't utter those terms. You know, we are we try to keep this course simple by not introducing all those complications. Okay.
Yes, sir.
So inductors in series in parallel almost behaves like the resistances when they are connected in series and parallel. Okay. So next thing is capacitors in series and parallel. So if you have n capacitors, C1, C2 to Cn, and they are connected in series, is it possible to find out an equivalent capacitance that is possible to equivalent capacitance for this capacitor?
Yes, sir.
Capacitor. Yeah.
Yes,
so
sir.
here you see
One by
Vs,
C2 is
Hmm? Yeah, so some of
Yeah,
these
the
things must be knowing
reciprocal
already.
sum.
Yeah. So if you find out, if you put the values of the capacitance that we already recapitulated, so for each of these capacitances, if you put the V1, V2 to Vn, so ultimately we end up getting a summation, because for each of them it is basically the same current. So integral I dt is the same. So ultimately it comes out to be the summation 1 by Cn n equal to 1 to n integral I dt t naught to t, and then the summation of Vn t0 n equal to 1 to n. So for the equivalent capacitance, it is 1 by Ceq. So integral t naught to t I dt plus Vs t naught. And from this, if you by comparing, so you get that 1 by Ceq is equal to 1 by C1 plus 1 by C2 plus 1 by Cn. Okay, so Ceq you can find out the reciprocal of 1 by C1 plus 1 by C2 plus 1 by Cn. So that is the capacitors in series. Similarly, you can have the capacitors in parallel. We can have the capacitors in parallel, and we can get the equivalent. So in this case of capacitors in parallel, the parallel capacitance, the equivalence is given by the direct summation. Okay, just adding the values of parallel capacitors gives the equivalent capacitor. So these things you must studied in your level, and just a recapitulation, and some of these proofs also you can do on your own. Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the next thing so these are many, anyway. These are just recapitulations. It is that will be, these all will be used off and on when we do the different types of numericals. If there are multiple circuit elements, resistances, capacitances, inductances in series, parallel, and if it is possible to combine them, you basically need this. Okay. And we have also seen for resistances we have shown that it is also possible to do the star delta or delta to star transformation and all, so which will also be applicable here. Okay, so we will see this when we do the other problems, when we actually combine RL and C together. So the next thing that we will actually study is basically RL circuits. Yes.
So delta and star conversion is also applicable for capacitor and inductor.
They will be applicable, but in a different way. We will see that.
Okay.
Right now we are studying capacitor and inductor as circuit elements. We have not seen that as a circuit element, but okay, we have mentioned that they are going to work when the voltage and current are time varying. But in what way they will act? Resistor.
Sir, your voice is not audible.
Sir, your voice is not coming.
Sir, you are not
Sir, you are
audible.
not
You are
audible.
not audible, sir.
Sir, we can't hear you.
But we have not seen here actually.
Sir, we can't hear you.
Sir, you are not audible.
Not audible, sir.
Not audible, sir. Audible.
Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
It got. Okay, so what we will do is now is basically the RL circuits. That means the circuits where so far we have been solving circuits for purely resistive, where the circuits were having pure resistances. But now we will have also another circuit element, which is the L. And this L, we saw that these L and C are such elements that can store energy. They have the capability to store some amount of energy, but but then again there is a difference. They are not like power sources where they can supply energy for a long time. Whatever energy is stored, they can release, and once it is, they cannot generate energy. So okay, so they are basically passive elements, just like R, but they have some limited capacity to store energy. And so since they work in the time varying, when the value of current and time varies, they also exhibit some other type of behavior that we will gradually see. And since they are stored energy, what actually will happen is, even when the circuit is switched off, they can keep on driving the circuit. Okay, because they have some energy stored in it, and until and unless that energy goes, they can still drive. They have the capability to drive the circuit. So you can see this circuit. Suppose you have a circuit consisting of R1, R2, and L as shown. Okay, all of you can see this.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
And
Yes, sir.
connected to a voltage source. Okay, and what is also shown is a switch. There is a switch which is showing with an arrow. So that means the arrow means the way to open the switch. Okay, so it is basically shows that at t equal to 0, the switch is opened. Okay, so it basically means that for t less than 0, the switch was closed. Okay, if the switch is closed for t less than 0, and then the switch is opened at t equal to 0, so, and then there can be a situation for t greater than 0. So you understand that suppose you are, in the time axis. So at t equal to 0, the switch is opened. So there are two situations. One, t less than 0. In 2t less than 0, it will be one type of circuit. In t greater than 0, it will be another type of circuit. And the transition is taking place at t equal to 0. So if you divide the time axis, you see that you are at t equal to 0 here. There is a situation when t is less than 0, then there is a situation where t is greater than 0. What are the situations? Suppose this, yeah.
Sir, have you showing anything? Sir, I can't see anything, sir. I just see only RL circuits in that slide.
What do you mean?
I can see what sir is showing. It's on your
Yes,
end.
sir.
The problem is on
I
your
can
side.
also see.
It is visible, sir.
Yeah, so if any such problem is there, you should solve it locally rather than because since most of the students are seeing, they are not commenting. So you understand the situation. There are two situations. One is this circuit, the switch is opened in electrical engineering language. This is called that the switch is opened at t equal to 0. Okay, so at t less than 0, the switch is closed. So the switch is closed is what is the circuit. So at t less than 0, this is the circuit. All of you can see?
Yes, sir.
At t
Yes,
less than 0, the voltage source is connected to R1. The voltage source is connected to R1, and then R2 and L are in parallel. So that is the circuit. Okay, so what is the going to be the current and all, we will come later. So let us first be convinced about the circuit configuration. So at t less than 0, this is the circuit, because that switch means this, that the switch is opened. So you see the direction of the arrow at t equal to 0. So this basically means the switch is opened at t equal to 0. But if see the direction was opposite, direction of the opposite was opposite, what it meant? If in this switch,
Closed at t equal to
Switch
0.
is
Sir, means after t
equal.
greater than 0.
yeah, so correct.
the
So
switch will be
we have to correctly interpret this switch, So the information is there. So currently what it shows is at t equal to 0, the switch is opened. But if this direction was opposite, that it would have meant that at t equal to 0, the switch is closed. Okay. So you have to read the switch very carefully. You know, when you are doing electrical engineering in whatever domain you go in future, you know, if you have to handle circuits, all the information will be there, and you have to make your interpretation. So for t less than 0, this is the circuit configuration. Because at t less than 0, the switch is closed. But what happens when t greater than 0? So
Switch is open.
the switch is opened. Okay, so as soon as you open the switch, you know, that voltage source is isolated from the circuit. So this voltage source is, because in any circuit you need a voltage source, that we have learned. Without a source, there is no question of a circuit. If you consider the, you know, in our country, if you just make all the wires and transmission lines, whatever you see, and you don't have any power station anywhere, then it is useless. Okay, so the source basically drives the circuit. So that we will come, but here, so this is the circuit configuration. So once we have a switch like this, we have to find out what are the different ways the circuit gets modified. So for t less than 0, you have this type of circuit. So the voltage source is in the circuit. Okay, but for t less than 0, the t greater than 0, the switch is open. The voltage source is, you know, is not connected in the circuit, but you only have R1, R2, and RL. These are in the circuit. Now we have a L here. Earlier we were not having L. Earlier we were having pure resistances. You know, whatever we have studied so far, and we could solve the circuits by KCL, KBL. You know, by, if required, the star delta transformation and all will be required to simplify the you know, circuits, and, you know, to combine the for finding out the equivalents and all. But now we have an L in the circuit, and as we already studied, that L is an element which can store energy. So you see, at t less than 0, this was the voltage source. The voltage source was, you know, driving the circuit. Okay, the voltage source was driving the circuit, and there was some voltage drop across R1. There was some voltage drop across R2, and so on. And due to this, there will be the energy stored in the inductor. But then suddenly there is at t equal to 0, you made the switching, and the source is taken out of the circuit. But you see, with the L, there is still a closed path. With the L, there is still a closed path. With the R2, sorry. With the R2, there is a closed path. And the inductor was storing energy up to time t equal to 0. And since there is a closed path, there is again, so the inductor will now drive the circuit till it becomes de-energized.
Your voice is like. Sorry, sir.
Audible or not?
Sir, it is audible.
Yes, sir, audible.
Yes, sir.
Audible. So also all those local problems you need to solve, you know. So this is the situation. I have still not shown the. So you see, for t less than 0, the voltage source is driving the circuit, and we will see how to analyze those circuits. Now, whatever is it is driving the circuit. At t equal to 0, the switching is made, and then it goes to this new circuit. So what happens is, at t equal to 0, whatever is the condition, that acts as the initial condition for the circuit at t greater than 0. The condition at t equal to 0 basically acts as an initial condition for the circuit for t greater than 0. So all those initial conditions we have just kept on writing. Okay, IT0, VT0, all those things we are writing in all those L and C equations. Okay, So the point of giving this example is for t less than 0, the circuit was in a certain configuration. And then some change was made. And then, so as soon as the change is made, so, in the earlier configuration, that inductor contains some energy. So that is the energy becomes the driving energy for t greater than 0. Okay, is it clear?
Yes, sir.
So,
Yes, sir.
once the inductor has energy, it will drive the energy. If there is a closed path, obviously, it will need a closed path to drive that energy, to dissipate that energy. If there is if there is no closed path, suppose this R2 was not there. Okay. Suppose this R2 was not there. So as soon as at t greater than 0, you open the circuit, there is basically no closed path. Okay. But since this R2 is there, R1, does R1 make a closed path? R1 part of any closed path?
No, sir.
No,
No, sir.
No, sir. So the
No,
but R2 and L, they generate a closed path. Okay, so and R2 is an element that can dissipate energy. R2 is just a resistance. It can be a coil. Okay, all our domestic heaters are basically some piece of resistance, so they can dissipate energy. Okay, now we have an inductor that has some energy. It was having some energy, and at t equal to 0, it was storing the energy, and then suddenly since the mother energy source, that is Vs, was removed, but the inductor had some energy, so that energy can still be used to dissipate. Okay, so inductor will basically result in still some current flow into the circuit, possibility of some current flow into the circuit because of its capability to store energy. It is not like an exactly as a battery source, but it has some capability. We'll see. We'll actually solve numericals and all, finding out the currents and all by this type of effect. And what we will actually see is all these values actually will become a function of time. Okay, because of this inductor and capacitor. So this inductor and capacitor are passive elements, but they have slight amount of storing energy. Now, this type of circuit, so you see what is happening in this situation. You basically have a circuit like this. You just have an R and L. Okay, you just have an RL and a current flowing through it. That circuit at the top, that I have shown. Yes.
So what is the meaning of passive element, sir?
The passive element is an element that cannot, drive anything.
Okay.
Okay.
Sir,
So that circuit at the top.
Sir, in a case where if R2 was absent and if we open the switch and remove the voltage source and again switch it on, sir, then will L again dissipate energy?
Yeah, then those things will happen, because for energy to flow, you need a closed path. Okay, so as soon as you generate the closed path, so whatever is the earlier initial condition, from there it will start.
Okay, sir.
Okay, so that is clear. So that circuit at the top, sir. I did not want to show in the beginning, because as soon as I showed it, if I had not discussed this example with R1, R2, and L, it would have become confusing. Okay, so the circuit at the top, you see there is a resistance and inductance. I have shown VR, VL, and then suddenly I have got a current. If I just suddenly showed that circuit, there would have been many questions. Where from is this coming and all those things. Now I kept this circuit after showing this example, but in the books will actually start with the circuit like this, that left hand side top, what I have shown, which is which may confuse the students. So I thought to introduce this, that there is a possibility of this type of circuit where you have a charged inductor and with some capacitor. Okay, and then it also forms a closed path. And as soon as it forms a closed,
So you're not audible.
You're not audible.
Not audible. Yes, sir, you are not audible.
path, it will.
Hello. Sir, your voice is not coming, sir.
Sir, voice is not coming, sir.
Technical issues.
Can you hear?
Yes, sir.
Yes, sir.
Yes.
So it got disconnected. So we have to basically analyze this type of circuit where there is an R and L and there is a possibility of residual current flowing due to the energy stored in the inductor. Okay.
Excuse me,
Sir,
Yes.
sir,
Sir,
the
if R2
direction of
is-
current should be from. Sir, in the uppermost left circuit, the direction of current is towards left, no, sir, if the inductor is charged.
Yes, sir. Same doubt.
It should be towards the left only.
Sir, if R2 is replaced by a zero resistance, then will energy be dissipated?
No, I think so.
No, then it
Can
won't
you-
be dissipated.
That's a
Can you
short
hear me?
circuit.
you
You'll
are
probably
not
get
audible.
fire.
Sir, can I leave?
I think there will be
Can
no
you hear me?
energy stored in the short circuit.
Yes, sir.
Yes, sir.
Yes, sir. If R2 is replaced by a zero resistance, then will energy be dissipated?
Then the inductor will not charge. I think.
Then the inductor will be short circuited.
The zero resistance.
Yes,
So
sir.
it will
If
be the
R2
inductor
is-
in itself. No, but you have to give the inductor some other element through which it will, dissipate. It will be just if it is alone, it will be just staying in the charge condition.
But sir, if the inductor R2 is replaced by zero resistance, then the inductor will not charge at all during the charging process.
But R1
Yeah, so
is
many
present, right?
things many things are there. Okay. So we will see. There are very interesting problems. Don't complicate those. Let us first develop the mathematics and then we will apply it to the problems. There will be a lot of problems in the book.
Yes, sir. Sir, also in the
can you-
second diagram, shouldn't the direction of current be along the same direction in which it used to flow in the inductor earlier?
Which diagram?
In the second diagram, the direction of current isn't that opposite? I mean, in the second loop.
That has to be actually found out. Well, we'll do in actual examples so that what will be the direction of current and all those things.
Okay.
We'll do
So
actual
we are
examples.
assuming just any general direction.
Yeah, right now we'll assume any general direction and then we'll see which one is positive, negative, all those things we'll have to. Obviously, some logic will be there. Yeah.
Sir, can you please explain the top left figure?
That is the figure I wanted to come at the end, but the point is that there can be situation where an resistance and inductance can be connected this way. And once they are connected and if there is any amount of energy stored in the inductor, there will be a current through that circuit. Okay, so there is a voltage across the inductor, there is a voltage across the resistor from the condition at t less than 0. And then
Sir, the direct
suddenly equal to the energy source is find out what is the current inside it. We'll actually do it mathematically. We'll find out the mathematics of it.
sir,
It is actually in the next slide. Yeah.
so the direction of current in the topmost left figure should be in opposite direction.
Direction.
Yes, sir.
we have kept some direction, but if it comes out, when given a particular problem, if it comes in the opposite direction, obviously it will be negative and all. So we solve a circuit by assuming certain direction, and then if it comes out to be opposite, you have to just change the direction. We have done in the problems also.
Okay.
If I show one direction and go ahead with the problem, and then the value comes negative, obviously it means it is the other way.
Yes.
So that we will see. This is just to show some arbitrary direction. So you basically have a condition like this. Now in this condition, what will actually happen is there will be a potential across the resistance, and there will be potential across the inductance. Okay, the potential across the resistance is basically given by Ri, and the potential across the inductance is basically given by L di dt. And in the whole loop, that VR plus VL is basically going to be negative.
Hello, sir.
Sir, your voice
Not clear.
Sir, you are not audible.
Not audible.
Yes, sir, not audible.
Going to be 0 because you don't circuit.
सर आवाज कट रहा है
Sir, I think your voice is not coming.
Not audible.
Can you see
Sir,
the screen?
from the very beginning of this slide.
Can you see the
Can you
screen?
repeat, sir? Yes, sir. Now we can.
Yeah. So since there is no voltage source, okay, the sum of Ri plus L di dt will do 0. And by solving this circuit under different conditions, so for this circuit, see what type of equation is this? What type of equation?
Differential. First order differential.
Linear differential equation.
first order linear differential.
Differential equation. Yeah, to solve, what do you need to solve?
IF into.
What do you need to solve?
And we can also solve it in another way also.
Variable separable or integrated.
Yeah, there are many methods.
Initial
Methods so ultimately the objective is to get some I. Okay, the
Yes.
objective is to get some I, and for that you will have to, what is required.
So here it is variable separable, but in general we can use integrating factor.
No, any
So if
method. I'm
the
telling
right
you.
side is 0.
Sir,
No, what
after
I'm-
solving, we need some constant will be decided by initial conditions.
Yeah. So what you basically need is some boundary conditions. Okay. Sometimes they are called initial conditions and all those things. So in this case, all the initial conditions will be the conditions at t equal to 0 because the switching took place. The switching took place at t equal to 0. So the objective is to find an IT that satisfies the above equation as well as IT0 at t equal to 0. So at t equal to 0, there was some current. Can you hear me?
Yes, sir.
Yes, sir.
Yes,
Yeah.
sir.
Yes, sir.
Sometimes I need some sound, otherwise I feel that as if I got disconnected. So ultimately the objective is to find out what is the current IT for t greater than 0. You had a situation for t less than 0 and at t equal to 0 some switching took place. So for the t less than 0 basically determined the condition at t equal to 0, which is going to act as an initial condition for t greater than 0. And we are interested to find out the IT for t greater than 0. So there are many approaches. You people will be experts in this for solving differential equation from your 12th class. So you have solved first order. You must have solved second order also differential equation. But this is just a first order equation, very simple. So one is the direct approach. You do the separation of variables. You take I on one side, di by I, and on the other side you are basically left with R and L, R and L and constants, the constant circuit values. So you do the integration from I naught to I. That means from at t equal to 0. At t equal to 0, the value was suppose I naught, and then you do up to some arbitrary I. And then what type of solution is this in this approach? It will be in what form?
Exponential form.
Exponential form.
It will be in some form. Okay, so it will be in exponential form or e to the power I naught e to the power something like that. There is another way is if you do the indefinite integration and substitute the initial conditions. You do the indefinite integration, you will get some constant. You put the initial substitute the initial conditions, and then you get the value of that constant, and ultimately you get the expression of IT, because our objective is our objective is to get the value of IT. So in the direct approach, you basically get IT equal to IT naught e to the power minus R by LT. All of you can do this?
Yes,
Yes,
sir.
yes,
Yes, sir.
Yeah, so all of you can do this. So IT equal to I naught e to the power minus R by LT. So there are different approaches. Indefinite integration also you can do. Here in the first approach, we put the limits. Indefinite integration should also yield you the same type of expression. Now, there can be a general approach. So basically the equation is Ri plus L di dt. Ri plus L di dt. And let us assume that let the solution be in the exponential form. Okay, so let us assume that we have a solution in the exponential form, like in the form ita e to the power st. Okay, what we are looking for? We are looking for an expression for it, because we are solving a differential equation, and we want to find out value of I, and obviously here the I is going to be a function of t. So let the solution be in the exponential form it equal to a e to the power st. So the objective will be what will be the value of a, which is basically a constant, and what will be the value of the st, which is in the exponential form. So if you substitute the assumed solution, in the equation, for Ri you can directly put the value of it, and for L di dt you have to basically differentiate. So the differentiating this will give you what? Di dt. What is the result of difference? As e to the power st. Okay, so as e to the power st. So you will basically get this type of expression. Ra and e to the power st is common. So you get Ra plus SLA together, and then multiplied by e to the power st is equal to 0. And just by dividing, so if you keep S alone, so you basically keep S equal to plus S plus R by L. So if you divide this whole equation by LA, you basically get S plus R by L A to the power st equal to 0. So what is the solution of this equation?
S is equal to minus R by
S
S
minus R
equal to
by
minus
L.
R by L.
How many solutions are there in this equation?
Two solutions.
Two
solutions. A is 0 or S is minus R by L.
I will be 0 and previous one, sir.
Sir,
How
for
many
S,
solutions?
there is only one solution.
Two,
for
sir.
S, only one.
What are
I think
what are the
infinitely many
variables?
solutions, because A can be anything.
Only S is the variable.
A equal to 0 is a trivial solution.
Okay.
A is equal to minus R by L is the only thing, like good thing. What do you call it?
Can there be any other solution? So you told maximum 2 solutions.
No, I don't think that. E is always
Sir,
positive.
we can put many things and we can get many solutions.
Many things and many solutions means what? I am asking what are the variables?
Sir, S.
In the assumed solution.
S and A are the variables.
S and A. So what are the possible values of S and A? What are the possible values of S and A that will make this equal to 0?
A equal to 0 is
S
1
equal
and
to
S equal to
minus
minus R by L.
Minus R by L.
minus R by L.
But if A equal to 0, then I total equal to 0. So I as a function of time, so it's trivial solution.
Okay. Any other guess? Any other student?
A cannot be 0. A cannot be 0.
Okay, A cannot be 0. Anything else?
Because I cannot be 0 always.
S plus
Sir,
R is equal to 0.
A can be equal to 0 because it satisfies the original equation. If current is 0, then di by dt is also 0, so equation is satisfied.
So A cannot be 0.
A can be 0.
No, sir, A can be 0.
A can be 0 is a trivial solution. If you
Yes,
put
it is a
A-
trivial solution, and it can be.
Sir, A is any
Like
real number
it
and
can
S
be,
is
but it's
minus
not
R
what
by
we are
L.
looking for.
we are not looking for. A can be 0, but we are not looking for. That will make a 0 solution,
Yes,
Working
sir.
with zeros is no good. We are looking for something finite.
Yes, sir. That's what.
So if you put S equal to?
Minus R by L.
Minus R by L.
So if you put S equal to minus R by L, okay, that makes it 0. Any other thing? Any other non-trivial thing?
A equal to I0.
Yes, sir.
A is initial.
No, that is okay.
So time can be minus infinity, but that is not
A
preferred.
can be determined by.
No, we are working on t greater than 0.
Yes.
We are now in the situation t
S
greater
can be
than
minus infinite.
X minus
Yes.
infinity.
But can you work with it? S equal to minus infinity.
It also makes I
No.
equal to 0
No, sir.
always.
So that is also a trivial solution. If you put in the solution S minus infinity, it will become IT 0.
Yes, sir.
Yes, sir.
0.
So
Sir,
what
but
are
S
the
minus infinity will become indeterminate form, na? Because it is
Yes, sir.
S
Infinity
is
by
also multiplied with it.
it
Yes,
is,
sir.
so
S
it will,
plus R by L.
Still
so
it will be 0.
if you put S equal to minus infinity, it will again make IT 0. Okay.
But it
But
is
it
not
becomes
indeterminate form.
intermediate form, sir.
It is not indeterminate form. It is exponential. E to the minus infinite. That is much smaller than the first part.
So e to the power minus exponential. So that is basically 0. Minus infinity, e to the power minus
Sir, S
infinity.
is also on the upper part, sir. So it is also infinity, and it infinity by infinity is indeterminate form, sir.
So these are the possible solutions. Okay, S equal to minus R by L, S equal to minus infinity, is A equal to 0 also. So, but if you put, we have just seen that if you put A equal to 0, it becomes a trivial solution. If you put S equal to minus infinity, so it becomes e to the power minus infinity, so that is also 0. So your IT becomes another trivial solution. Okay, so you cannot work with this solution. Neither can you work with this solution. Okay, so though they are for this above equation, these are the possible solutions. Mathematically, if you ask a mathematician, they will all give these solutions. You have been doing this in your school. Okay, but we are actually solving a circuit. We are actually trying to find out a variable, how the current value changes, and if you cannot work with zeros because it will actually change. So the only, can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Yes.
Yeah, so the only realistic solution is S equal to minus R by L.
Yes, sir.
Okay, so your IT becomes A e to the power minus R by LT. Your IT becomes A e to the power minus R by LT. Obviously, A and all has to be found out, but we have found out a good value of S. Now, once IT equal to minus R by LT at T equal to 0, amount of current was flowing.
Sir, you're not audible. Yes, sir.
Sir, you are not audible.
Sir, you are not audible, sir.
No.
Hello.
No, sir.
Why is not
Wait.
equal to 0, sir?
Can you hear me?
Yes, sir. You are audible.
Yes, sir. Now.
Yes, sir.
Yeah. So at t equal to 0, there was some current, which because and that current was there because the circuit was.
Sir, the
Hello. Can you hear?
Yes, sir. You are audible, sir.
Yes, sir.
Visible?
Yes, sir.
Yes, sir.
So now you are not audible, sir.
Sir,
Not
you are
audible, sir.
not audible.
Sir, you are not audible.
आज बहुत प्रॉब्लम है.
Give holiday today, yaar. Only 40 minutes remaining, yaar.
Please.
At t equal to 0, your I was equal to I0.
You are not audible, sir.
Sir, again, you are not audible.
Sir, you are not
Hello,
audible,
sir.
sir.
Kamal sir, please inform Alok sir that he is not
Yeah,
audible.
I'm doing that. Please. Everyone, please mute yourself. Bajaj, mute yourself.
Can you hear?
Yes, sir.
Can
Now
you
you
hear?
are audible.
Yes, sir.
Yes.
Yes, sir.
Yeah.
Yes, sir.
Can you see the
Yes, sir.
screen? Yeah. Yeah. So
Yes, sir.
IT
Screen
is equal
visible.
to I0 e to the power minus t by L by R. So we have an RL circuit, and we got this current greater than in a certain form I naught e to the power minus t by L by R.
Sir, your voice is cracking, sir.
So if we substitute, can you hear me?
Yes, sir. We can hear you, but your
Sir,
voice
Yes,
is
sir.
cracking.
Yes, sir. You
your
got it.
voice
Yes,
is
sir.
cracking.
Your voice is cracking,
Time
sir.
after time, sir.
Yeah. So if we
Finishing after
substitute,
time interval.
what is happening?
Sir, actually, your voice is cracking a
So
lot.
your voice, sir.
I
Due to
don't
the
know.
internet.
I am normal, but whatever if there is a network disturbance issue, I cannot help. So we can assume this L by R to be equal to some parameter called tau. So ultimately we get this IT by I naught. So IT by I naught equal to e to the power minus t by tau. Can you see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So IT by I naught equal to e to the
Sir, you
power
are not
minus t by.
audible.
Not audible.
Sir, you are
No,
audible.
sir. You're audible.
So IT.
Sir, you are audible.
So IT by I naught equal to e to the power minus t by tau, where we have defined tau as equal to L by R. Okay, so L by R, whenever you are having one L and one R in the closed loop, that we define one new parameter tau is equal to L by R. Now this IT by I naught equal to e to the power minus t by tau, if we plot this. So what we are doing is we are plotting IT by I naught versus time versus IT by I naught. Where will it start? At t equal to 0, what is the value?
1.
1.
Maximum.
So at t equal to 0, the value is 1, and then what? How will it proceed?
Exponentially
So it
decrease
will
to
keep
0.
on
It will
decaying.
exponentially decay. It is
Decrease
having
from zero.
exponential.
It will become the asymptote.
So it is having an
Its value
exponential
will
nature.
only between 1 to 0.
Okay, so it will from 1, it will start from 1 equal to at t equal to 0, and it will exponentially reduce. Okay. Now, if we find out that IT by I naught, since it is a function of time, if we find out the derivative of IT by I naught at t equal to 0.
Sir, 1 second. Can you please show the previous slide? Last line I just missed.
Last line.
Yes, sir. That previous slide, last line I missed. Last two. Yes. Thank you, sir.
So this IT by I naught, it is a function of time. It is exponentially reducing, starting from 1. So we have done IT by I naught. We have normalized it. So its maximum value is 1 only. Okay, because the magnitude is 1, and it exponentially reduces. Now, if we find out IT by I naught, if we do the derivative of IT by I naught at
Minus
t equal
1
to
by tau.
Minus R by L. R by
minus
L.
Minus 1 by tau.
minus 1 by tau.
Minus
And
1
if,
by tau.
and if you substitute tau by L by R, so you get basically equal to minus R by L.
Yes, sir.
So what is the physical meaning of ddt of IT by I naught?
Tangent to this graph at t equal to 0.
Tangent to this graph. Correct. What is the
Slope
name?
of the tangent.
Slope of
Yes.
the tangent. What is the name?
Rate of decrement.
Okay. So it is basically the tangent of the graph at t equal to t naught. T equal to 0. So what we have done is there is the IT by I naught reduces exponentially, is starting from 1, and we have found out the tangent. Tangent you can draw many places. Everywhere you can keep on drawing the tangents. But what we have done is we have just drawn the tangent at t equal to 0, where the graph starts, where the characteristic starts. Now, since this is the tangent, you see this tangent also hits the t-axis, the time axis at a particular place. Okay, so what does it mean? What does it mean? That if this IT by I naught is reducing at a particular rate, it is reducing exponentially. So if you find out the rate at which it is.
So you're not audible again.
Sir, you're not audible.
Sir, you are
Yes,
not
sir.
audible.
Sir, you are not audible.
That you are not audible.
It is irritating.
Sir, again
yaar.
you are not audible.
Sir, you are not audible, sir.
The point where it intersects the time graph is tau only.
Yeah. If it decreases
Yeah,
at the beginning rate, this is the time where it will be 0.
Yeah, right.
Will it be tau?
I think sir disconnected.
Yes.
I think half an hour is left.
Because I
Should be
think
holiday. It is irritating, isn't it?
Everyone, please mute yourself and wait.
सर है
सर नहीं है, सर आएगा। म्यूट करो,
ओके
वेट करो।
प्लीज म्यूट योर
ओके
Can you hear me?
yes sir
yes sir
Yes, sir. Sir.
Yes, sir.
Yes, sir.
Can you see the screen?
yes sir
yes sir
Yes, sir.
Yeah.
Yes, sir.
So yeah. So if you draw the tangent at t equal to 0, so basically means is that it by I naught, if it reduces at that rate, it will become 0 at a particular times where the tangent hits the t axis. Okay. So this is the time where the tangent will, if the decay follows at the same rate as the starting instant at t equal to 0, then it will hit that time axis.
so you're not
Hello,
audible
sir.
again
sir you are
again
not
not
audible
audible.
Sir, you're not audible.
Okay. So how?
Sir, your voice. Sir, you are not audible again.
Sir, you're not.
Can
hello
you see?
yes sir
So
yes sir
in this decay,
you are not audible
Again audio gone.
क्या हो रहा है
if
Still
the
not
decay
audible.
factor is initially, what is the
एक एक वर्ड सुनाई दे रहा है.
Can you see the screen?
yes sir
yes sir yes sir
Yeah. So the point is
Yes,
how
sir.
much is the time at
So your voice is flickering.
Sir, your voice is
is that
cracking again
voice
and
is not
again.
clear.
Sir, your screen is not visible, sir, and voice is also cracking.
because you huh?
sir your voice is not clear
Yeah. So you have
सर बस दिख ही रहा है सुनाई नहीं दे रहा.
hello
hello.
yes,
yes
sir
sir
Can
now
you hear me?
now you're audible
Yeah.
You are audible.
Yes sir,
So
now you are audible.
so how much is this time at if it decays at the same rate?
tau time constant
So you have basically found out the gradient t naught t equal to 0.
Sir, your voice is
So
cracking.
basically
sir.
this okay one is basically this magnitude by this t is basically equal to the slope. Okay. So from here you can find out this t is equal to L by R. Tau.
Your voice is not audible.
the voice is lagging
This tau. So this tau is basically called the time constant of the circuit. If you have an L circuit, L by R is basically having the unit of time. It is called the time constant. Can you hear?
Sir, we can hear at times only.
Yes, sir.
Sometimes your voice is
Sir,
coming very
I'm
cracked.
unable to see your slides, sir.
And sir, it is very difficult to put up all those cracking verses. Means, can you please just start from this
Yes,
page?
sir. It is very difficult to
Yes, sir. Start
understand.
from
Your
beginning.
voice is cracking a lot.
Most of the words are not audible.
Okay, at least you.
Again,
So
I am
this.
unable to see the slide of sir.
Slides are visible.
You are not audible, sir.
Hello, sir.
Hello.
Sir are not in meeting
Yes, sir.
now.
Which meeting?
In this meeting.
Can you hear?
Yes,
Yes,
sir.
sir.
Yes, yes, sir.
See the screen?
No,
No,
sir,
sir.
not yet.
No,
No,
sir.
sir.
no, sir.
No,
No,
sir.
sir.
No, sir. No, sir.
Seen now?
No, sir.
Yeah,
Yes,
yeah.
sir.
Now it can be seen.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
No, sir. Sir, I'm not able to see.
Hello.
Sir, your screen is not visible and or you are not audible
Leave the, me-
to.
leave
Screen
the
is
meeting and
visible, but
rejoin
audio
again.
is not coming.
पेपर क्लिक करवा दे.
Hello.
Sir, you are not audible.
Sir, you are not audible, sir.
Again, audio gone, sir.
Everyone, please mute yourself. Your voice will be recorded.
Kamal sir, sir, can you request sir to send the PDF files? We are not able to study afterwards.
Sir will send you. Okay, I will also ask him to send.
Yeah. Can you see the screen?
Yes, sir.
Yes,
Yes.
yes,
Yes, sir.
yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
Sohail,
Sohail,
please
please
mute
mute yourself.
yourself.
कौन बोला ऐसा?
Sir, not audible.
Everyone, please mute yourself.
Who is beatboxing?
Hello, everything is
Please
going to
don't
be
do it.
monitored and will affect on grades. Classroom behavior also considered. So please.
क्या बोल रही हो? हाँ. फैन कहियन की सुतल
Can you? Hello.
Yes, sir. We
Yes,
can
sir.
see now.
Yes, sir.
Yes, sir. It's
Yes,
visible.
sir.
Slide
Yes, sir,
is
you're audible.
Can you see the screen?
Yes,
Yes,
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So
Yes, sir.
this so you take down the definition of time constant, that
Sir, now
is
the
the
screen is
time
more.
taken for I.
Yes, sir. It is visible.
Time taken for I by I naught to drop from unity to 0, assuming a constant rate of decay as the decay rate at t equal to 0.
Hello, sir.
Ah,
Sir, you're not audible.
I'm not speaking anything. Can you see the screen?
Yes, sir.
Yeah. So
Yes,
so
sir.
if you put this it by I naught at t equal to tau, if you put in this expression e to the power minus t by tau, if you put t equal to tau, you get e to the power minus 1, whose value is, if you use a calculator, you can find out 0.367. So it basically means that at t equal to tau, the value of the magnitude, the it by I naught, actually decays down to 0.367 of the maximum value. Okay, so
Yes,
that is
1
how.
by e times that value relaxation.
Yeah. So but the actual definition of time constant is the time taken for it by I naught to drop from unity to 0, assuming a constant decay rate of decay as the decay rate at t equal to 0. That means at t equal to 0, at whatever rate it was decaying, if we follow that rate, at the time at which it will become 0 is called the time constant of the circuit. Okay, and we will see that it will have a lot of applications in usage. Lot of times you will encounter this term time constant. Clear? Can you hear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
So you just see, I have left one message in the chat box. That also you see. Okay.
Sir, will the timing be informed through mail?
I will inform.
Okay.
It will be in that additional slots in the evening. So there can be a lot of problems. So suppose that you are given a numerical like this, that you are given a circuit like this. So you see, it is a circuit. There are 2 resistances and 1 inductance connected, and in the central leg you have a battery of 12 volts. Okay, and you now understand the switching, that at t equal to 0 the switch is opened. So the battery was connected at t less than 0, so it was connected, and suddenly at t equal to 0 it was opened, that means the battery is taken out of the circuit. Okay. Problem is clear? All of you can see?
Yes, sir.
Yes,
Yeah.
sir.
So what are the possible circuits? So there can be a t less than 0 condition, and there can be, so this is the circuit at t less than 0. The same circuit but the battery connected. Okay, at t less than 0, this is the circuit. The battery is connected. So you know, very simple circuit, you know what to solve it. And this is what type of source is it?
DC
Voltage source.
DC source.
DC source.
DC source. Constant. DC source.
Sir, independent DC
Constant
voltage.
DC.
Voltage source.
And independent as well.
DC source. So DC, what will be the effect in the inductance?
Sir,
Initially it will get charged.
No,
the
sir,
direction of
inductor.
current will be reversed.
No, my
Just
first
after the
question is, will there be...
Screen is not visible, sir.
Inductor will not store energy because it is DC, sir. Di by dt is equal to 0.
Yes, yes, yes.
Hello, sir. Are you speaking something?
Sir, you are not audible. Where are you? Hello.
But there will be decay in the circuit.
Again, audio
So
got.
there will be di by dt.
We are not visible your screen and you are not audio also not audible.
But initially
Hello.
inductor is charged and then it will start decaying at t equal to 200 millisecond. Hello?
I am unable to see the slides. Is anyone able?
Yeah, it is
No,
Yes,
visible.
it is visible.
No.
Slides are visible, but they're stuck.
No. Slides are visible,
Sir,
but
not
audio is not coming.
Slide is not visible to me.
Slide is visible to.
Same here.
But for me the slide are not
Now
visible.
only 10 minutes are remaining.
Anybody can see the slide?
I can't
Yes,
see
it
Yeah.
is visible.
Yes.
Yes.
Slide is visible.
Lights are visible.
There is no slide.
Can someone
Only
please ask
sir
what
is not
will be the timing of the extra class which are going to be conducted on Saturdays?
He said he'll
I think
mail
it
us
is the
about
last slot.
Not yet informed.
Saturday we get
Timetable it
time.
was mentioned.
Can you hear this? Can you see the screen?
No, sir.
No, sir.
So we can hear but
No
cannot
sir.
see.
No, sir.
No sir.
No, sir.
Yes, sir, we can
Okay,
see.
yes, sir.
Yes sir. Now it's visible.
Yeah. So this is one situation when the t is less than 0. What will be the current through the inductor?
2.4, sir.
So 2.4.
2.4 ampere. Okay, because it is a DC.
2.4.
Similarly, you can find out what is the
2.4.
current through the 40 ohm resistance. Similarly,
0.6.
so that is basically the IL0, 2.4.
Yes, sir.
Because the t less than 0, that will be the current keeping on flowing, and suddenly you change the switch position. Okay, so that will be the current through the inductor at time t equal to 0. And say Vt less than 0, because see the question is find the voltage V at t equal to 200 milliseconds. So basically this value of this voltage V across the 400 ohm resistance has to be found out. But for t less than 0, the whole 24 volts is applied across it. Okay, so for t less than 0, it is always 2.24 volts. But we have to find out what is the, what happens when t greater than 0. Okay. Clear?
Sir, how will be
Yes, sir.
current 2.4?
How will we get 2.4 ampere?
Yes, sir. How will?
So in this condition, what is the current in the inductor, in this circuit? What is IL?
Initially, it must be 0, no?
No, what is the current in this through the 10 ohm resistance?
Because of inductor, it must be 0. Inductor is short circuited at that time, no?
Yeah, that DC.
T equal to
because it is
minus
DC.
and at 0. At T equal to 0, it's 2.4.
Okay, so for t less than 0, always this current is flowing, constant current is flowing because it is to the 10 ohm resistance. So its value is 2.4.
Inductor is charged, sir.
Huh?
Inductor is charged or uncharged?
It is getting charged. It is for t less than 0, it is the current is, but it is a DC battery is connected.
Sir, is it 13 volt?
Hmm?
Hello.
Now for
Sir, it is
T,
13 volt.
which one?
Sir, answer
13
13
volt.
volt.
So answer is
Sir, 16 volt.
12.99218 volts.
So 16
No.
volt I'm getting.
Okay, we'll see. So now for t greater than 0, so you see we draw the circuits. If it is different circuit, we will have to draw it and we will have to the initial conditions which will come from the previous circuit. So for t greater than 0, this is the circuit. For t greater than 0, this is the circuit. Okay, and
Yes, sir.
now this current IL, so the current IL was flowing through this. Earlier the current IL was flowing through the inductance. Okay, and now this current again continues to flow through this at t greater than 0. Okay.
Yes, sir.
You are not audible.
I'm unable to hear you, sir.
Sir, you are not audible.
So you basically have a
Sir, you are not
Your audio
audible.
is cracking, sir.
Sir, can you begin from starting? Initially, you were not audible.
Kamal sir, please tell Alok sir to start from beginning.
Kamal sir is also not
For
audible.
this slide, na? For this slide, na?
Yes,
T greater than
yes,
0.
sir.
Yes, sir.
Okay.
can you see the screen?
Yes, sir.
Yes, sir.
Yeah. So now if we
Yes.
apply the, somehow we have to solve the circuit.
Sir, students are asking to repeat this slide from the starting onwards. Because
I
there
can
are
repeat, but there is a lot of interruption. So this is the circuit, and the switching is done at t equal to 0. So there will be a circuit for t less than 0 when the 24 volts is part of the circuit. Okay, so then this is the circuit.
Hello, sir.
24 volts is a DC source.
Hello, sir. Your voice is cracking, sir.
Sir, you are not audible.
Not at all audible.
You see the screen?
Yes,
Yes,
sir.
sir.
Hello.
Yes,
Can
sir.
you- Yeah.
Yes, sir. Now you are audible.
For t less than 0, this is the circuit. And since this is a DC source, the current through the inductor, so inductor will not have any effect. So the current through the inductor is basically 24 by 10, which is the 2.4 ampere. And for Vt less than 0, anyway, this whole voltage is applied across this. Now there is a condition for t greater than 0. This is the situation for t greater than 0. And there will be some current because now the so to find out this current, what we have
Anyone hearing this background noise?
Yes.
Yes.
do is you have to
Audio
apply
gone
if you
again.
No, again the audio.
Sir, you are
is
not
cracking.
audible.
Voice is not clear.
Sir, your voice is not clear, sir.
can you see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, so if you apply this KVL, because this is how the your answer is being asked with the V, with the positive terminal, with the top terminal positive. Okay. So in this way, if you apply KVL, it is plus V, then minus 10 IL minus 5L DIL dt. So that is the
Hello, sir.
Sir, your voice is not audible.
Sir, not audible, sir.
Sir, you are
Can
not
you-
You are
visible.
not audible.
Can you see the screen? Huh?
Yes, sir.
Yes,
Please
sir.
someone
Your
to-
voice is not coming, sir.
So IL is equal to what? You see, IL is flowing in this direction. IL through the 40 ohm is flowing from the bottom to the top. Bottom to the top, but we have assumed V positive on the top. Okay, so your IL is basically equal to minus V by 40.
Yes, sir.
Okay, IL is equal to minus V by 40. So if you substitute this in this equation, so you will ultimately get this. So I'm substituting here. So V becomes minus, IL becomes minus, so we are substituting this in terms of making it effectively in terms of V. So keeping the V as it is, if you substitute this, you get here 10 into V by 40. So 10 by 40 into V plus 5 by 40 into dV dt. 5 by 40 dV dt. So ultimately combining them, you ultimately get this. dV dt plus 10 V equal to 0. Clear?
Yes, sir.
Yes, sir.
So dV dt plus 10 V equal to 0, which you can solve. So it will have a solution of the form V equal to A to the power minus 10t. We have already done this, that V equal to A to the power minus 10t.
Sir, can't we
Okay.
use directly current equation?
Yes, sir.
Huh?
I equal to I naught e to the power minus
I
RT by
equal to
L.
I naught.
You
yes,
can
sir.
do by I
direct-
also.
Yes, sir. Yes, sir.
You can also find methods also. Okay, so at V at 0 plus. So at 0, it was 24 volts up to this for t less than 0. So exactly at 0 plus, what is the voltage? What is this V? So what has happened is that t equal to 0, suddenly there is a reversal of current. This is the current is. So can you anybody tell what is that V0 plus?
16.24.
Minus 24, sir.
Sir, 16.24. No, sir. V0.
24.
V0 24. Huh.
24.
96.
Minus
24
it will be
96.
96 it will be 2.4 into 40.
96, sir.
96.
Yes, sir.
Minus
Now
96.
16 is coming. 90.
No, it will be positive 96.
Yes, yes.
I think sir's voice is gone again.
Pressure.
It is 96.
What we have asked now?
Sir, it is minus 96.
Can anyone tell me?
Sir, it is minus 96.
Sir, as for the voltage at time t just greater than 0, 0 plus.
It is minus 96, na?
Sir
current
is
is
asking
reverse
about
direction.
voltage across
Yes,
40 ohm
96.
resistance. 40 ohm
Yes.
resistance.
Is the screen visible? Screen visible?
No, sir. No.
It's 24, no?
No, sir.
No, it is minus
Across
96,
40
I
ohm,
guess.
it's not 24. Across 40 ohm, it's 2.4 into 40. Na?
At
Yeah,
t
so
equal to
time-
0, it's 24. But slightly
What sign
greater
will be
than 0,
negative,
it
I
won't
guess.
be 24.
Answer
Yes.
is 12.992 or minus?
No, 12.992
Plus
is after 200
12.99.
millisecond.
Yes.
Just after t greater than 0, it's 96 volts.
But I think that is also in minus sign. Minus of 12.9992.
No, I think it's positive. Let's see what sir's answer will come.
So when current will flow across
The value will
resistor,
be
then,
negative.
create a lesser potential.
The value will be negative as per the diagram.
Yeah, minus 96. Yeah.
Minus 96 by E squared.
Yeah. So let us stop today. We will discuss this example in the next class.